Welcome! These videos were recorded while I taught Econometrics over Zoom, but they were edited so that the student faces the questions and my answers to those questions do not appear. That explains why you may notice some unnatural transitions and why the videos are shorter than a normal lecture. But hopefully you enjoy them anyway. Bye now. We're ready then to start lecture number 9. This is the first lecture that includes material that will be part of the final, not the midterm. So we're starting sort of like the second part of this class. And in particular, we're starting something that I call part 2, which is topics, and we'll see a variety of different topics as we move along. In particular, one per lecture. So again, just to set expectations right, one, the pace is going to be faster than what we've been doing so far, because it's the transition from lecture to lecture is going to be tougher. Okay, we're just going to go from one lecture to the other one, going through different topics, and perhaps the tools and the concepts from one lecture will not translate immediately to the next one. And then second, I of course, if you say, oh, you're going to teach one lecture on nonparametric regression, it's clear that, or one lecture on RDD, it's clear that you will not be able to get into the details. So I don't intend to do so. My intention is to highlight the topic, give you an introduction so that you get exposed and know what the main things are, then show you some details within that topic that I think are relevant. Okay, could be derivations, properties, or sometimes some discussions that are more advanced. And then sort of like leave you in this place where you know more or less what the topic is about, you know the main ingredients, and then if tomorrow as a second year student you want to take a class on these topics or you want to inquire more, you sort of like know where to start, okay? As opposed to just take one of these, I could take, I don't know, RDD and teach 3-4 lectures, and so you will know a lot about RDD, but then you will not know about these other topics, okay? So just so that you know where we're going with this. Okay, so today we're going to start with nonparametric regression. And so sort of like, again, past and future is part 1. We were very coherent, and we talk about linear regression, interpretation, properties, endogeneity, IVs, and some panel data, which included also difference in differences. And now part 2, as I said, is topics, and we're going to start with nonparametric regression, which is something that you need if you want to really understand, for example, RDD, which is going to come next. And then we're going to realize that all these are prediction tools. So we're going to bring some more recent stuff in, let's say, machine learning. So classification of regression trees, or CART here, is something that we're going to talk about, and random forest. And then we're going to sort of like deviate a bit from this nonparametric methods for conditional means, and sort of like connect with linear regression when we talk about the lasso. Okay, that's about the topics that we're gonna, some binary choice we're gonna do, which is gonna be related also to classification here. And then once we're done with this second part of topics, we're gonna get into the third part of this course, that is gonna be inference. Okay, so there we go. So setup. Today we're gonna have two random variables, y and x. For simplicity today, just I'm gonna take y and x to be scalars. Okay, everything that I'm gonna say works for cases where these are potentially vectors, if you just do component wise, or traditionally where y is a scalar and x is a vector. Okay, p is gonna be the distribution of y and x. And as I said, the case where we have covariates will just affect some of the properties of the things that we're gonna talk about, but not mainly the derivations that we're gonna do. We're gonna discuss that later. And today we're gonna be interested in the conditional mean of y given x. We're gonna call this conditional expectation m of little x, which is the expected value of y, conditional x being equal to little x. And we're gonna assume that we have an ID sample from this distribution P that we're going to denote y1 x1 dot dot yn xn. So first comment that I want to make is that today and this literature in particular belongs to more, I would classify more this as a prediction problem. Okay, you're just trying to, given an x, say something about what's the y, in this case, the conditional mean. Okay, and so if you think about, we're not doing linear regression, we're doing, of course, non-parametric regression. But if you think and you go back to the first lecture that we did, conceptually, we're more in the territory of the second interpretation where we talk about best linear predictions and so on. And so here the goal is give me x, tell me what the y is. This has nothing to do, for example, with causality. When I say nothing to do, it means that these are not tools that are thought to make causal analysis, although eventually we're going to be using some of these tools for causal analysis because, for example, think about something like the average treatment effect. If there are x's floating around, the average treatment effect is going to involve conditional expectations of y given x. So if you care about estimating something like the average treatment effect, which we know admits a causal interpretation, then you may want to be using tools, okay, that are good for predicting the expected value of y given the treated and the expected value of y given the untreated, perhaps conditional on other characteristics. So then these tools that we're going to describe today and in the next few lectures are going to come up useful. But if you look at, where the literature starts, it's just a prediction problem. Give me the x's, tell me what the y is going to be. Okay. In the case where x is discrete, suppose that x takes L values, okay, then this is a very simple and trivial problem. You will define your estimator m hat of x as the average of the y's for, observations that have x equal to little x divided by the total number of observations that have that value of the x, okay? And this, I wrote here, is a natural estimator of m bar, because if you write in the discrete case, how this conditional expectation looked like, you're just going to be, again, noticing that we're replacing expectations with sample averages, and that's what we're doing. And then, actually, this estimator over here has all the expected properties that you would expect, like consistency and asymptotic normality, provided that you have certain, that you can say that the probability that x is equal to little x is positive for all these values, that you have finite second moments, and so on, which I would call regularity conditions, nothing special. So this is straightforward whenever you have x's that are discrete, which, again, sometimes happen. And one case that we've done so far is, for example, when these x is binary, okay, in the treatment effects case. But now we want to move beyond this. So one problem is that when x is continuous, as I wrote here, the event that x is equal to little x has probability 0. This is not a problem for the definition of the conditional expectation, but it is a problem for, how we may want to estimate the objects. In particular, following a strategy where you divide by the number of observations equal to that value you care about, it's not going to work out because you may have 0 observations essentially equal to that value, perhaps only 1. So this feature here, that x is continuous, affects the properties of the previous estimator. So we need to do something else. The first thing we're going to do is we're going to assume that this conditional expectation is continuous, okay? This will allow us to start thinking about the problem by saying, okay, I'm not going to be able to observe a lot of observations equal to a specific value, but I can find observations that are close to this value. And if the conditional expectation is continuous, then observations that are close to this value will be informative about the conditional expectation at that particular point. So the first idea that you may naturally think is something called Q nearest neighbors estimator. Actually, sometimes in the literature, you will find this as K nearest neighbor estimators. I don't want to use K because I'm going to be using K for something else. And so whenever I use this type of stuff, I always use the letter Q, which you'll see in other papers as well. So let JQ of X be the set of indices, okay, from 1 to n, or in the set 1 to n, associated with the Q closest to X values in your sample. So take a value of X. Suppose that little x is 1. Well, what is JQS? Gives you the indices of all the Q observations in your sample that are closest to the value 1. And so the Q nearest neighbor estimator is defined as the average of the outcome for those Q observations. Okay, So JQ can be formally defined as follows. You define the distance between each observation and the point that you care about. I said 1 before. And you're going to denote the order statistics by D parenthesis 1 and so on. So JQ is just going to be all the i's such that the distance does not exceed the qth order statistics. And then that's how you do it. When you start working with Q nearest neighbors and order statistics, sometimes, the definitions that you need for coding things, if you were going to implement this in the computer, are more sophisticated than the intuitive ones that you will use if you just want to think about this problem. For example, think about the point 1, then all you're doing, if you just think in the real line, it's just move to the right and to the left until you're gathering Q observations. When you just gather the Q observations that there are the closest that are to 1, you just take those Qs, see what the outcomes are, and then you take an average of those. Okay, so that's the Q nearest neighbor estimator. So the step 1, you find the Q observations with values of the sample that are closest to the point that you care about. In step 2, you average the outcomes of those observations. Done. The intuition is that if the conditional expectation M of X is smooth, then it should not change much if you move X, in a small neighborhood. And so the observations that are close but are not exactly the point that you want have information about your point M. And so what you will notice immediately is Q here is a tuning parameter. And so if you set Q equal to the sample size, for example, say, okay, let me just take all the observations. Well, in this case, this Q nearest neighbor estimator becomes just the sample mean of Y. Okay? And so as I wrote here, it produces a flat estimated function. The variance here is very low, but the bias is very high for many values of X unless M is truly flat. To see this, you can just think about this in terms of a picture. Suppose that here you plot M of X, and then here you have your X. And suppose that M of X is something like this. Okay, well, if you estimate this function, okay, with the sample mean, say that, let's assume that this is Y bar N, then what happens is that for some of the points, okay, we're going to have that the bias is very small, like here, low bias. But for some other points, the bias can be very big. This is high bias. And this would be for the point X prime, and this is for X prime. So, choosing Q very big has this effect that you have an estimator has low variance because you're using a lot of observations. Okay, but it gives you potentially high bias depending on the shape of M, right? If the true M is rather flat, you see here this area, like the M is kind of flat, then this works like charms, okay, in this example. But, if M is just really steep and so on, something like this, it's just going to work really poorly. So the other extreme is you say, okay, I'm going to just use Q1, just going to use the closest observation to the point X, okay, and then I'm going to report that Y as my estimator. Well, your estimator is just going to look all over the place, right? So if you plot it, it's just going to be points that will look like this, whatever. Not in this example, but you can see that it's just going to be so volatile. So in that case, there are a few observations, and so the variance of your estimator is going to be high. Of course, the bias is going to be small because you're just going to be using the best possible observation for that. So at the end of the day, as it is the case with all the tuning parameters that we're going to be talking in the second part of the class, there is typically a bias variance trade-off. You want to choose something that doesn't give you a bias that is too big, doesn't give you a variance that is too big. One way to trade these two is by looking at things like the mean squared error, right? Which is the bias square plus the variance. And a lot of these methods later on, like here I said, you could choose peak by using cross-validation. Those methods will rely on minimizing objects like mean squared error. Okay, so there is a flip side to this Q nearest neighbor estimator. Okay, Q and N stands for Q nearest neighbor. Q nearest neighbors, the estimator takes an average according to the Q observations that are closest to X, okay? So the number of local observations, meaning the ones that are close to the point that you want, is always Q. As you know, you're choosing that. You're saying, I want the Q closest observations to my point. Let's say Q equal to 5. You say, I want the 5 closest observation to my point. That's it. Those are the observations that you use. However, what you cannot control is the distance, of those observations to the point that you care about. So if you define something like H here, which is the maximum distance out of the Q points that you're using, well, this H is going to be random because you just choose the 5 closest, but there's no way you can guarantee, unless you impose assumptions and so on, as how close these 5 observations are going to be. In particular, how close the farthest one, the 5th one, is going to be to the point that you care about. So an alternative approach is to do exactly as I wrote here, the flip side, which is, okay, let's just fix a distance, fix this H, and consider all the observations that are within a given distance, okay? And now, the number of local observations is going to be random because I want to be fixing a window. I'm going to say, okay, I want to consider a window of size, say, plus 0.1, negative 0.1 from my point. If my point is 1, all the observations between 0.9 and 1.1. And then, I set a fixed window. Now H here is not random. It's just a window that you set. But then now the number of observations that fall within that window will depend on the distribution of X, and it's just going to be random. So, and one thing is important is that you can control both. Either you set the number of observations that you want to use and you let the distance free, or you just set the distance and you let the number of observations that fall inside to be random. So I'm calling this the bin estimator, right? Why? Well, if you look at the bin estimator, it just looks like this. M hat is just going to be the average of the outcome of all the observations that fall within my window divided by the number of observations that are in that window. So you can actually write it as a weighted average estimator. So you can write this M hat as a weighted average of the outcomes where the weights just take this form. The weights, over here are just these objects. Right? This is the WIX. So it's a weighted average. And so these are weights. They're all positive in this case, or 0, meaning they're non-negative, and they add up to 1. So M hat is a weighted average of the outcome. Okay? So for example, again, you pick the point number 2, and then you set H equal to a half. What is M hat X? Is the average of all the y's such that X falls between 1.5 and 2.5. And this is what this estimator is doing. You set a window, you compute the average of the y's. If you want to see graphically what this is doing, well, here you see, here you have some dots, okay? Forget about the lines right now. Just look at these black squares. So the black square is the bin estimator of the conditional mean at 2. So what is it doing? First, like here in this example, I'm setting the bandwidth equal to a half, as I said before. So this is 1.5 and this is 2.5. And so you set everything that falls in here, which are these points. This one, 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 this one. And then you take an average of those. And what you obtain is this black square. And that's your M hat. Set a window, find the y's, take an average of those y's. So then, if you were to like plot this, then it matters how fine of a grid you do for the X. If you use a coarse grid, you obtain a step function thing. Like if you use just 2, 3, 4, 5, 6, and those are the values that you do, then you would sort of like do some type of extrapolation, looks like a step function. Okay. And then if you set a fine grid and then you start looking at values that are like 2, 2.01, 2.02, and so on, and then you evaluate this formula on this fine grid, then you start having a smoother line, which is this solid line over here. And that would be the bean estimator for the conditional mean. Questions? All right, so let's keep going. Kernel estimator. So I wrote here, one deficiency of the bean estimator is that it is discontinuous at points that are equal to one of the points in your sample plus minus the bandwidth, okay? Because, it's an indicator function. And so when you have the indicator kicks at the boundary, if you just move a little bit, then you add a point or remove a point, and then that introduces discontinuity. The source of discontinuity is that weights are based on indicator functions, as I said. So the idea is that if we want to avoid this, and then this sort of like conceptually is a problem, just because, we did all this under the assumption that the conditional mean expectation was continuous, okay, the M function. And now we're obtaining, as a result of that, an estimator M hat that is discontinuous as a function of X. So that's kind of like unpleasant. So the idea is that perhaps instead of using these indicator functions, we use some form of continuous weights. This may lead to a continuous estimator of the conditional expectation. The family of weights that we're going to use at the end of the day are called kernels. And in particular, we're going to pay attention to second order non-negative symmetric kernels. Okay. So what is a second order non-negative symmetric kernel? It's a function, okay, that maps, in this case, the real line to the real line and satisfies 4 properties. The first one is that it integrates to 1. This is the definition of a kernel or a weight, okay? Second one is that it is non-negative. That's why it says here non-negative kernel. This makes the kernel non-negative. A third one is that k of u is equal to k of negative u, okay? And this makes the kernel symmetric, okay? The last one is that if you define this parameter here, kappa 2, okay, which is the integral of u squared times the kernel, okay, this is finite and non-zero. And this makes the kernel second order. So these are 4 properties of the kernels that we're going to use. And so the first thing, that we're going to see is that this bin estimator that we defined before actually can be expressed as something that is a function of a kernel. One thing to note is that this definition of kernels do not include the notion of continuity anywhere. It doesn't say anywhere that the kernel has to be continuous, okay? So if we care about, using continuous weights, we'll have to impose that separately. So, kernel estimator. I wrote here, note the definition of the kernel does not involve continuity. Indeed, the bin estimator, which is the one that we used before, can be written in terms of a kernel function. So define this kernel as 1/2 the indicator of the absolute value of u being less than or equal to 1. Okay, I'm defining this estimator. This is called the uniform kernel on -1, 1. Okay, and so know that we have these indicators that are xi minus x less than or equal to h. I can just move this h to the other side. So I can write this as xi minus x divided by h less than or equal to u. Okay. And then this is just 2 times this kernel that I define over here. Okay. And so then you can write this estimator exactly like this. And if you see, it's just the definition of what we're going to call a kernel, nonparametric kernel estimator of the conditional mean, which is just the average of the outcomes weighted by the kernel divided by the sum of the kernel, okay, across all observations. And this is a special case, with this particular kernel of the so-called Nadaraya-Watson estimator, okay? And this bin estimator that I've been calling bin estimator is also called, a Nadaraya-Watson estimator with a uniform kernel. So what's the definition? Then the Nadaraya-Watson kernel estimator is let KU be a second order kernel and H be a bandwidth. Then the Nadaraya-Watson estimator is defined as M hat. And then this formula over here with K is any kernel that satisfies the 4 properties that we said before, and then you have Nadaraya-Watson estimator. So it's also known as kernel regression estimator or local constant estimator. Both of these terminologies are popular, okay? And then some people will say Nadaraya-Watson, some others will say kernel regression, some others will say local constant estimator. And then we're going to see in a minute why local constant makes sense once we start talking about local linear. Bandwidth, H, okay, plays the same role as before. If you just pick a large H, so you make a large window, you use a lot of observations, okay, so you get smoother estimates, but they may have high bias, okay? So as H goes to infinity, actually this Nadaraya-Watson estimator converges to the sample average, okay? Same way as the Q nearest neighbors using all the observations. If you set H too small, then you have getting estimates that end up being very erratic, okay? They have low bias, but they have a lot of high variance. So actually, if you take H to 0, your point prediction of the conditional mean of Y at Xi, condition on Xi is just Yi, just that observation, and that's what you say. Popular kernels that are continuous, okay, and that people use are the Gaussian kernel, which looks like this, or the Econ kernel, which looks like this. And there are others, okay, but arguably these two are the two most, or among the two most popular kernels that people use. And there are different reasons. The Gaussian is because it is natural to use, and the Asymptotic because it has some optimality properties when it comes to the properties of these Nadaraya-Watson estimators. However, as we'll discuss later, typically the choice of the kernel doesn't affect the performance of the estimator too much, and at least not relative to the importance of choosing the bandwidth well. So it's not surprising that people, meaning people doing theory and researchers doing applied work, will pay a lot more attention to how to be careful about how to pick the bandwidth, more so than how to pick the kernel, which you just use one of these twos and then you're good to go. So the one thing that I want to do today is to talk a little bit about these asymptotic properties and how you get them. Okay, and so this is going to take us some work. It's not going to be like a full careful proof, but at least it's going to have the main ingredients. And I would like to illustrate at any point in the derivation what type of assumptions we're using and where do they kick in and so on. And hopefully the idea is that later when we talk about notions like undersmoothing and things like that, these derivations help us understand, those discussions that are important, okay? Okay, to recap, we wish to show this expansion over here. We're going to show that square root n8 nh times our estimator minus the truth can be decomposed in two terms, okay? One that I'm going to call delta 1, the other one that I'm going to call delta 2. And delta 2 is going to be a nice term, meaning it's going to be asymptotically normal, centered at 0 with some variance. And so this is a term that gives us the usual asymptotic normality. And then delta 1 is not going to converge to a normal. It's just going to converge to a constant, and it's going to give us a bias. So the first thing that we're going to see is that all these estimators are asymptotically biased, okay? And so we're going to do this now. Question is, why would NH be the rate of convergence? If you just look over here, and then if you think about it, this is at a point X, okay? If you ask yourself, how many observations are you using to estimate the conditional expectation at H? Well, just a fraction of your data, right? You're just using a window and you're looking at the observations that are in that window. So effectively, n times H is the effective number of observations that you're using. Say your sample is 1,000 and then H is 0.1. You're going to be using 100 observations to estimate the conditional expectation at a given point, not 1,000. And so that's why you'll see that in nonparametrics, the rate of convergence is always dependent on the bandwidth. So this, the asymptotic framework that we're going to use is one that now requires three things. The first one is that we're going to let the sample size go to infinity. We want an approximation for a high sample size, sure. Actually, you notice immediately that at every point we're using NH observations. So we want NH to go to infinity because we want to estimate each particular point sufficiently well asymptotically. That's the approximation that we're going to use. And then the other one, of course, is H going to 0. As we have more data, we want the bandwidth to be smaller so that we're using better and better observations. Or if you want closer and closer to the point, where like if our sample size is like huge, okay, then you would imagine that you will be able to just consider observations like really, really close to the point that you care about. And as I said, I'm not gonna go over all the tricky details of the derivations, but I'm just gonna go over a sketch of the arguments. So are we ready? Good. So let's do this. So we're gonna do the expansion. We're gonna start by writing. Well, let me change the color here. We're going to start by writing y as m of xi plus ui. Okay, this I can always write this. Okay, because I simply just take y and you add and subtract. I can write this here. So you take yi is equal to yi, and you add and subtract the expected value of yi given xi, which we're calling m. That's all you're doing. And then we're defining u as the difference between y and the conditional expectation. So by construction, this expectation is 0. So if you want to do it again, this expected value of yi given xi plus the difference between yi minus this conditional mean. So it's just notation, what we're doing here. So, and then we're going to let sigma square x be the variance of u conditional on xi. Here, u is defined in terms of our manipulation. And then we're going to write this thing over here, which is now I'm going to add and subtract not m of xi, but m of x, the point that we care about. All the expansions that we're going to do are a particular point m of x, okay? And so this is this point is going to be fixed as we go. Okay, so we're going to look now at the numerator of m hat. So this is going to be 1 over nh, a sum from 1 to n of the kernel xi minus x divided by h times yi. And what I'm going to do is I'm going to replace yi by the expression that we have above. Now I'm going to split this into the 3 terms. There we go, where I use that. Let me write here where recall that the nonparametric estimator of the density of x is just 1 over nh sum of the kernel. So I use that in this line over here. And then what I'm going to do is I'm going to call this delta 2 x hat, and this one over here delta 1 hat x. So now, if you move things to the other side, you have the m hat m minus m of m. It's just going to be delta hat 1 x divided by f hat of x plus delta hat 2x divided by f hat of x. And this is the first piece of our expansion. Where I just divided by f hat everywhere to get to the last line. But now we have expressions for these two terms that we are going to be deriving. And so one, as you can see, this lambda 2 is a term that depends on this error term u, which we know is mean 0 and has some finite that we're assuming variance if we assume moments of y later. And so this sigma square is going to be finite. So this term clearly, just think intuitively will give us a center limit theorem. Whereas this term over here, it just captures the fact that to estimate m of x, to say something about m of x, we're not going to be using m of x. We're going to be using m of xi, okay? This idea that we're using observations that are close, and this gives us a bias. So this term will determine the bias in a minute. So what we're going to do in the next few slides is to analyze this delta 1 and delta 2 sort of like in detail. We're going to start with delta 2, okay, which is easier. So what I wrote here at the top is the same expression that we had in the previous slide. And I want the expected value and the variance of this delta 2 hat. So let's start with expected value. Expected value of delta hat 2x is expected value of 1 over nh, the sum from 1 to n of k xi minus x divided by h ui. And so this is 1 over h, expected value of k xi minus x h ui, and this is 0 by the law of iterated expectations, because expected value of u conditional on x is 0. So expected value, quite straightforward. One application of the law of iterated expectations, you get the expected value of this term is 0, as expected. Then we want the variance of this guy, which is just the expected value of this square and if we use the law of iterated expectations again here, what we get is 1 nh squared expected value of k xi minus x divided by h sigma square xi. Law of iterated expectation, again, because we define expected value of ui squared condition xi as sigma square xi. It's a definition. So now I'm going to write this down as an integral. So I'm going to write this expectation as an integral. So it's an integral with respect to the distribution of x. So let me just, whenever you see xi, I'm going to use the little z to avoid confusion with the little x. And so the variance of this term, you can write like this. And what we're going to do next is to use a change of variables where we're going to let u be equal to z. Yes? Yes. Thank you. So we're going to define u. Again, why am I doing this change? Because remember that when we define the kernel, we said, what's inside the kernel, we call it like u. Well, let's make that change of variable. So notice that you can then write z is x plus ux, h, sorry. And so dz is h du. We're now going to use this change of variables in this integral over here. Are we good here? I'm going to keep going. All right, let's do this. So what is here? Well, I conveniently rewrite what I had before. Whoops. So this is exactly what we had before. And as I said, we're going to use this change of variables, which again, you can rewrite here z equals x plus uh. So if we do this, let's do it. You have the variance of this delta hat 2 term. It's just going to be 1 over nh square integral k u square times sigma square x plus uh times f of x plus uh du, and there's an h here is, remember that dz is or let's do it here, whoops, here du is 1 over h dc, so that means that there's gonna be here an h that is gonna cancel out with the square that we have over here. Okay, so now we're going to use two properties. Let's write them in a different color. I'm colorful today. So sigma square x plus uh equals to sigma square of x plus little o1 as h goes to 0. Since this function sigma square x is continuous. So I haven't written the assumptions yet. So I'm going to write them when we write the actual theorem, but I'm going to be using assumptions as I need them. Okay, so the first thing that I need is, well, I have sigma square x plus what I really want is sigma square x. Okay, so I need to assume that this function here is continuous. Okay, for this argument here, the same thing happens with the x. So, or with the f, sorry. So I'm going to assume that f is continuous. Then later, actually, I will have to assume that f is differentiable. actually continuously differentiable. But for now, just work around with continuity and then replace this back into the expression. And then you have that the variance of this delta hat 2x is 1 over nh times the integral of k square u. And then here you're going to have something that looks like this: sigma square x plus little o1 times f of x plus little o1 du. And this is 1 over nh, the integral k square u times sigma square, whoops, okay. Oh, sigma square x f of x divided by nh times the integral k square u du. These u's are awful. Well, that one's not much better, but okay. And then all the other ones are small terms. This all little O1s multiplied by things and O1s and O1s. There's a 1 over NH multiplying all that. So what we get is that this variance takes exactly this form. So again, we just took the expression that we had. We did the change of variables. And then we exploited continuity of these two functions so that we could get the functions at the point that we care about. And so what we have then at the end of the day is that the variance of this delta 2, sigma square h, f of x, nh, and the integral of the kernel square du. And then there's a reminder. Okay. This integral that we see over here, this one, is called the roughness of the kernel. And we're going to denote that by the RK. Okay. And so when you put all the pieces together, you get this. The variance of this term is sigma squared times f times the roughness divided by nh plus a reminder. And now you have all the pieces that if you put together, you can invoke CLT, if you assume moments of y, which is going to be part of our conditions in a minute. And then you can claim that it's square root n nh delta hat 2 converging distribution to a normal with mean 0 as we described, and this variance sigma square f roughness, which is what we derive. Okay, that's the easy term. So are there questions about this one? So let's get to the other term. This is a fun term. Okay, so here we have this delta hat 1, okay, which is the term that we derive, and as I said, captures the bias. Okay. And so we're going to do like a similar trick. Okay. So let me just find the expectation of this guy. Expectation of delta hat 1, I should write x, is 1 over nh expected value of k xi minus x divided by h m xi minus m of x. And again, the object here that is random is the xi. So I'm going to write this as an integral. Sorry. Of course, this n disappears. I'm going to write this as an integral. So it's going to be k z minus x divided by h m z minus m of x f of z dz. And not surprisingly, I'm going to do a change of variables again. It's going to be the integral of k u. Man, I need to work on my u's. M x plus u h minus m of x f of x plus u u h du. So here we have this object, and now let's bring back colors. We're gonna say, okay, look at this m of x plus u h minus m of x. This is a difference between the function at x plus u h minus the function at x. And this is the conditional expectation, the one that we said before. We're assuming that it is continuous, okay, so that we can do use local approximations. Well, here we're going to assume a lot more. I'm going to assume now that this function is twice continuously differentiable, and I'm going to do a Taylor expansion. So that gives me that I have here m prime, the derivative, at x times uh plus 1/2 m prime prime x u square h square plus a reminder twice continuously differentiable. This will give me a term that is going to be smaller than h squared. And I'm going to assume that the density of x is continuously differentiable. So again, Taylor expansion, the density at x plus f prime of x uh plus little o h. And so here comes the messy part. The messy part is that, whatever you see here, m minus m, you have to replace for all this. Whatever you see f, you replace for all this, okay? And then if you do that, you have expressions, you start working the cross products. But let me just help you a bit with something. When you multiply, you essentially have two that you care about. Those that are linear in x, in h. What is linear in h? Well, this one is linear in h, okay? When you multiply that by this. What else is linear in h? Nothing else, because the rest are all smaller. So you have that this is f of x m prime x u h, okay? And then you have the ones that are quadratic in h. And what are these? Well, if you multiply, for example, this one that is linear in x with this one, that's quadratic in h. So we have m prime x f prime of x u square h square. What else? Well, this term is quadratic in h. So when you multiply this term with this one, you get quadratic in h. So you have 1/2 m prime prime of x times f of x u square h square. And that's it. All other products are little o h square. Go to 0 faster than h square. So even though, as I said, if you just write this product and start working all the terms, you're going to have a long thing. At the end of the day, there are only two terms that really matter. One is the one that is linear in h, keep saying x. This one, and the one that is quadratic in h. This one. Okay? But again, going back to, we're going to take stuff out of the integral now as well, based on the previous question that I got. And again, the continuity assumptions, these are like smoothness assumptions. are the ones that allow us to get these expressions in the integral that depend on u. And we're going to replace with some that don't depend on u when it comes to the function m and f. So you see here, f depend on x, the derivative depend on x, the derivative depend on x, f prime depend on x, x, x. These functions do not depend on u. Nice. Let's put everything together. And now this is what I did. I just replaced this expression and this expression that we wrote and work out the products, okay? So, which I don't want to do in writing, but it's essentially what I said. And so what you have here first is that this first integral, and this is cool, is just 0 because of the kernel, because the kernel is symmetric. That is 0. And this collects all the terms that are linear in H. All the terms that are linear in H get multiplied by an integral that is 0 out. And then you have the terms that are growing or going to 0 at rate h squared. And that includes all this stuff over here, which in principle has this integral that appear in our definition of the kernel. We denote by kappa 2, and then we said this is between 0 and infinity because it's a second order kernel. Okay? So, and that multiplies this term here that collects the stuff that we had before, and the rest are smaller. So what do you get? We get that this expectation is just h squared times kappa 2 times the density times this term that we're going to call b of x, which comes from the term that actually collects the bias. And then these terms that collects the bias is actually quite intuitive because it is related to the second derivative. And the second derivative gives us, how much the slope of this thing function that we're trying to estimate changes, right? So if the second derivative is really large, then it's going to be harder to find observations that are close to each other, right? So not surprisingly, this depends on the second derivative, and it also depends on the first derivative and how the distribution of x works around that first derivative, which is captured by the density of x. So the part that I'm not going to do today, this is why it's a sketch, is the variance of this term. You just work the variance of this term. It's a similar expansion, slightly longer, but you show that this variance actually goes to 0. So this guy converges to a constant. What is that constant? This. And that's it. So what you conclude is that square root nh, this term minus a constant, conversion probability to 0. In other words, square root nh times this, well, no, this is the asymptotic variance, whatever. I was going to say something that is wrong. So now you put everything together and you have this theorem. And this is the one that you should remember, even if you won't remember anything else, okay? So what does it say? It says, suppose that f is continuously differentiable at the interior point x and it has a positive density. We're using both of this because f appears in the denominator. We use it in one of the steps for the integral. Good. M is twice continuously differentiable at x. We use that in our expansion, twice continuously differentiable. Sigma squared positive is continuous at x. We use this as well. K is a non-negative symmetric second order kernel. We use all of this throughout the proof. Then we have 2 plus delta moments for y, which is what gives us some application of CLTs. Okay, so when I apply the version of the central limit theorem that we need, requires 2 plus bounded 2 plus delta moments. We're going to use that. And so then lastly, you have n going to infinity, h going to 0, and h going to infinity, and I have this condition over here. What is this coming from? Well, it's coming from the previous line. Okay, so you want this object, the bias, not to explode. And so here you have square root nh times h squared, which you can write as square root of n times h to the power 5. So forget about the square root. You want this to be bounded. And that's saying that nh to the power 5 should be bounded. And that's the condition that we have here, so that the bias doesn't explode to infinity. And so you put everything together, and what you have is that your estimator minus the function that you're trying to estimate minus the asymptotic bias is asymptotically normal with mean zero and variance given by this. Okay? Well, if you were not paying attention or got distracted, we were dividing everywhere by f. Okay? And so that's why before we had sigma square, the roughness times the density, but you're divided by the density, so eventually the variance is the density squared. They cancel out. This appears in the denominator. Okay? And that's a theorem that gives you the asymptotic distribution of the Nadaraya-Watson estimator. Okay, that was it for derivations for today. So that's that. But now we need a lot of interesting discussion, unless there are questions before I move to discussion. Excellent. So what is the asymptotic mean squared error? Well, you can use exactly the same manipulations that we did, okay? Believe me, just a little bit more algebra, but nothing more sophisticated than that. And you can show that the mean squared error of this estimator takes this form over here. And, you know, it's the same objects. The kappa of the kernel, the B that we define, sigma squared, the roughness, the density, all the same objects. Of course, it's the bias square plus the variance. And now the cool thing is that this depends on H. H appears here, H appears here. And the cool thing is that it has the intuition that we said before. If we increase H, if we increase H, yes, then, you know, we lower the variance, which is this term over here. This would be the variance, right? But if we increase H, we increase the bias. Here's the bias square, right? And H appears in there. So then you can say, okay, let's choose H to minimize the mean squared error. And what you obtain is a constant times n to the negative 1/5, okay? And so you obtain a bandwidth here that satisfies our HO to the negative 1/5, okay? Because that's what the optimal mean squared error is doing. So this is the same rate that you obtain in density estimation, okay? And the constant C here, well, depends on all these objects, the kappa 2, the bias term, sigma squared, the roughness, the density, okay? And then it may take some expression that looks, you know, more or less ugly depending on the setting. Here is not too bad, but we don't need to write it up. And then what you could do is, you know, now you have, this is your optimal bandwidth, and it depends on this constant that depends on these things, okay? Whatever, times n to the negative 1/5. And then you can say, well, I know this. I don't know all this constant. You can put hats, and so on, and then you get the optimal bandwidth. And you can do that. You know, depending on the setting, could be cumbersome because remember, here's the funny thing. This term B, okay, B of X had inside M prime of X and M prime prime of X. And this is kind of like a problem, right? Because you started off saying, I want to estimate the function M non-parametrically. And now to compute the optimal bandwidth, you need to estimate the derivative of that function, the second derivative of that function. And, you know, derivatives, you know, as a general rule, are harder to estimate than functions. And as a general rule, integrals are easier to estimate than functions. Okay, so, you know, of course, there's a huge literature on how to obtain optimal bandwidth in nonparametric regression. But the usual stuff is that as you to estimate bandwidth optimally using, you know, plugin approach, you will have to estimate functions that are more complicated than the ones that you started off with. So there are other methods like cross validation, okay, that are maybe easier to implement. So but in this class, I'm not gonna talk about cross validation because we don't have time. Okay, so if you have never seen or heard of cross validation, this is not a class to learn that. Okay, sometimes we teach that in 481. I think Joel does it, and depending on the class that he covers, but definitely is in some of the courses in 481. But it's not something that I want to teach in this class. I'm just simply I want to mention this here because stuff like cross validation is popular and used a lot. So if you're ever exposed to this and you want to see, well, okay, where should I start? It's a good point to just at least know that there is such a thing and there's typically a viable option in this particular problem of choosing the bandwidth. So comments. The kernel choice, not super important as we said before, but you see that it depends, it appears here in the roughness, right? The roughness depends on the kernel, and this kappa 2 also depends on the kernel. So you can say, well, give me a kernel that minimizes the roughness, okay? And then you show that the Epanichnikov kernel is the one that gives it the smallest roughness. And that's why sometimes people will just opt to use that because of that particular reason. Then bandwidth is a larger problem. I wrote here the constant C for the optimal bandwidth depend on the first and second derivatives of the mean function M. So, when the derivative of the function is large, the optimal bandwidth is small. When the derivative is small, the optimal bandwidth is large. And then this is intuitive. Imagine you're estimated a function that is roughly flat. We know that the best that we can do is the sample average. And so the sample average essentially is taking a huge bandwidth. So that is flat. When the function is really, really steep, okay, you can see that the minute that you deviate from the point that you care about, the value of the y is just going to be very far from the one that you care about. So, when the function is very steep, you want a bandwidth that it is small. Okay. And then in this setting, it's less obvious than it is perhaps to obtain reference bandwidth like Silverman rule of thumb, so rule of thumb bandwidth. Okay. Just because in non-parametric density estimation, you could say, well, let's assume that the density is just normal at that point, and that gives you everything you need to get a rule of thumb. And in this context, it's less natural, okay, because it depends on this function b here that depends on first and second order derivatives of the conditional expectation function. So it is less common in non-parametric regression to use just rule of thumb bandwidth. For the comments, the bias term. The bias term needs to be estimated to obtain valid confidence intervals, okay? Because otherwise you cannot do a confidence interval. You need now two things to estimate, the bias and the confidence interval. But again, the bias is annoying because it depends on this B term that depends on M prime, F, and F prime. And so it's typically, and they may perform poorly in finite samples. And if you estimate all this, they may change also the asymptotic variance. All these issues are advanced, not topics that I'm going to cover here, but I do want to leave you with the idea that if you want to deal well with the bias and the variance and so on, there are results out there. This literature is fully worked out, but you have to be careful and you need to understand what the problems are. So I'm not giving you a full description of what these problems are. I just want you to make you aware that there are these problems related to the bias terms and how to estimate them that you should be aware of. Okay, so the one thing that a lot of people do, okay, is to use a trick that is called undersmoothing. Okay, and I'm not gonna say whether. Okay, let's just describe what it is, and then I can tell you what I think. But in a way, it's just ignore the bias. Okay, you're gonna say, look, estimating the bias is problematic. It's annoying. It takes a lot of work. So let's just don't do it. So, and I'm gonna argue that we should not do it by saying that, whatever optimal bandwidth you gave me, okay, from your computer, from optimizing the middle square error, I'm going to choose one that is actually smaller than that. And what do you mean by smaller? Well, I'm going to pick one such that n square root n h squared goes to 0. Okay, so remember, because the bias was square root n h squared kappa 2 b. And if you're telling me that this goes to 0, then that means that the bias is 0. But this is saying here, again, if you write this as square root n h to the 4, because I bring it inside, and so you have n h to the 5th, and then you're telling me that this is little o1, well, you're saying that h is little o n to the negative 1/5. So it's smaller than the one that you obtain from minimizing mean square error. So this creates a problem because optimal choices, okay, by minimizing the mean square error, by doing cross-validation and so on, are incompatible with this idea because they will give you a bandwidth that will satisfy this property as opposed to this property. Okay, so what people do is they just get the bandwidth from, say, cross-validation, whatever, and then just pick a smaller one by either changing the rate or multiplying by something that is smaller than 1, and so on. What happens is that in many settings, under smoothing ends up not working well in finite samples. And then in some settings where, the theory is not sufficiently developed, perhaps doing something like under smoothing is something that, is the only option that you have. But in this particular literature, there are a lot of methods available today and better options than doing under smoothing. So some of these papers are recent, meaning perhaps in the last 10 years. And there are a lot of econometricians that have worked out better ways of doing inference in nonparametric regression by taking into account the bias and estimating the bias, or by, accounting for, the extra terms that you have in the expansions explicitly, and so on. All this, as I said, are advanced topics. But if somebody says under smoothing, then I want you to understand that they essentially say you come to this theorem over here, and then you just pretend that this doesn't exist. And look, now I have square root n m hat minus m converges to a normal with dot c mean 0 and that variance. Okay? And then you don't have to estimate any bias whatsoever. That's what you're doing when you're saying under smoothing. Finally, we have the curse of dimensionality. So far I've talked about the case where x was a scalar, but in reality, most often you have that x's have high dimension. Or, high dimension, I don't mean in a machine learning sense. I'm just saying higher than 1. So I'm going to use dx here. I've been using k so far in this class, but now k is the kernel. So for today, the dimension of x is going to be dx. Okay, and so now when you do the Nadaraya-Watson, okay, you will require a kernel for each of these covariates. So that gives you dx bandwidth. A bandwidth for each of these covariates. But in reality, people don't just choose a bandwidth for each covariate. They just pick the same one for all the covariates. And so you have that the rate now just going to be n times h to the power dx. And this is the so-called curse of dimensionality, because the dimensionality of the x's is the exponent in the bandwidth, and it affects the rate of convergence. And it says the higher the dimensionality, the lower the rate of convergence. And when you look at it, you're looking at this formula, and remember that I talk about effective number of observations, okay? If you now have 10 covariates and you're gonna be taking windows in each of these 10 covariates, and then you're gonna see, okay, what are the effective number of observations that I have? If for each covariate I take a window and I take the cross products of these windows, well, the number of observations are going to be really small. The more covariates you have, the smaller the number of effective observations that you're going to have. And that is a problem for the rate of convergence of this estimator, okay? So notice that this is not a computational problem. Sometimes it could be a computational problem, meaning like, oh, I don't have observations, okay? I just have cells, if you want, that are empty. That's a computational problem. This is a theoretical problem. It's just telling you that the rate of convergence is just going to be really slow. And the larger the dimension of x, the worse the rate of convergence that you're going to have. That means the much larger the sample size you're going to need to have any reasonable, form of convergence. And that's what curse of dimensionality is. Curse of dimensionality affects all the non-parametric estimators, okay, that are known in a way, unless, you start using something called dimension reduction or whatever. There are tricks that, again, are beyond the scope of this class. But, even modern or more in vogue methods for estimating conditional means, okay, like the random forest and so on, that have a lot of bulk, they still suffer from the curse of dimensionality. They will have to perhaps deal with the problem in different ways, okay, and have tricks to alleviate these problems somehow, but the problem is still there. FX is just conceptually, if you have many x's and you're looking at cells, well, you're going to have few observations in the cells, period. Questions about this? What are the limitations of the Nadaraya-Watson estimator? Well, it's funny because if you impose a linear conditional mean, so suppose that m of x, this is a population, this is the truth, it's actually linear in x, the Nadaraya-Watson estimator sometimes doesn't perform very well there. Okay, so even in fact, if you just give you a straight line, okay, no error, Nadaraya-Watson estimator still performs poorly if the distribution of x is not uniform. Okay, so you start having cells with fewer observations than in other cells, and so on. So, and that's the reason for that is that this Nadaraya-Watson estimator at the end of the day is trying to estimate things with flat functions. Okay, and so that's one issue that we're going to discuss in a minute and see if we can get around it. But that would be the first lesson. The second one, and more important for some of the topics that we're going to see next week, in particular the regression discontinuity design, is that the Nadaraya-Watson estimator performs poorly when you're estimating a function at the boundary. The theorem that I gave said that x was an integer point. But suppose that x, whatever, supported on 0 and 1, and then you want to estimate the conditional expectation at 1. Well, that's a boundary point, and the derivations don't work anymore. You have to do different derivations, and the order of bias, okay, is of order h, and it used to be in the derivation that we did of order h squared. Remember, h is going to 0, so it was much smaller, but now it's much larger. Okay, so. What's the reason? Well, imagine if you're just estimating at a boundary point, say 1, you don't have observations to the right and to the left to do like an average of what's going on at 1. You can only use observations, say, from the left. And so that creates a problem. Okay. And so you can show at the end of the day that the estimator, not only has a big bias term, you can show it's just inconsistent depending on what you do at the boundary point. So if you care about the boundary point, then the Nadaraya-Watson estimator is not a good choice. And then you can say immediately like, well, when do we really care about the boundary point? Well, I'm telling you, one case where everything is about the boundary point is the regression discontinuity design, which is a design that is quite popular in economics. Okay, so you do care about the one boundary point. So if I'm telling you that we do care about the boundary point and that this performs really poorly at the boundary point, then what can we do instead? And the idea of that is to use local linear estimators, which is the last topic that I'm going to cover today. Questions so far? I know I'm going fast, and I know that today is more material than other lectures, but I intend you to go and look at the lecture notes and these slides again so that you can revise everything. This is not a lecture that you're going to get 100% just by listening to what I'm saying. All right, last part, local linear estimator. So the Nadaraya-Watson estimator is often called local constant estimator, and it locally about x approximates the here CEF is conditional expectation function as a constant function. Okay, so why? Well, you can write that this Nadaraya-Watson estimator that we wrote solves this minimization problem. You minimize the distance between y and a constant. Okay, the distance meaning here the difference between y and a constant square, where the criterion function is weighted by the kernel. So this is a weighted regression of y on a constant. That's what this Nadaraya-Watson is doing. I mean, I'm not going to show this, but it's just, I'll solve this optimization problem. The solution is exactly the same Nadaraya-Watson that we wrote before. So, having different interpretations of estimators is convenient because typically it informs you about what you're doing, even if you don't see it immediately from the original expression. So, no, without weights, this estimation problem reduces to the sample mean. Just remove this, you solve this problem, you get the sample mean. So the Nadaraya-Watson estimator generalizes this to a local mean. So what we're doing is essentially is computing local averages, which we know, determined by these weights, okay? So the idea is we may construct alternative non-parametric estimators of the conditional mean by alternative local approximations. What if instead of doing a local mean, I do a local linear regression? Okay. Well, that leads to the so-called local linear approximation. And this is a popular choice and is the dominant choice, for example, in topics like RDD. What is it? Instead of approximating m locally as a constant, the local linear approximation approximates m locally by a linear function. Okay? And the estimation is locally weighted least squares. So this is what you do. You find the intercept and the slope that minimize this optimization problem. What is it? Well, if you remove, suppose that you ignore the kernel here, this is just least squares where, you're recentering x by the point that you care about, okay? But you're not doing that because you're just also weighting by this kernel. So the local linear estimator of the function is the intercept. Okay. And the local linear estimator of the derivative of x is given by beta 1. So one automatic benefit of this approach is that you get both in one step. So you get the object that you want, the local linear estimator, but you also get an estimator of the slope, which you may need, for example, to compute something like the bias and so on. We know that appears somewhere. So, and notice that you can write this local model like this, okay? And then using the regressor as xi minus x here makes that the intercept is equal to this conditional expectation, right? Because if you grab this representation here, you compute the expected value of yi given xi given to little x, well, that is beta naught because this guy is just going to be 0. And you see why the intercept is giving us the conditional expectation, driven by this recentering that we do over here. And you can solve this by least squares because it's just a weighted least squares. And that is something that is often convenient because, we'll see it gives us some nice closed form representations. Now, in terms of going back to the picture that I did before, you see that now what you're doing, if you just pick a bandwidth, as we were doing before, okay, so I'll pick a bandwidth of 1 here, and then the 0.2, the estimator is a square. What you're doing is doing least squares here, least squares here, and least squares here. Provided you're in each of these brackets, you're just doing least squares that are weighted because you're weighting all these observations differently by the kernel. But that's exactly what you're doing. Before we were doing flat lines, now we're doing linear lines. Okay, and I wrote here what we have at the end of the day is a linear regression fit in each region, okay, where the observations are weighted, in this example, by the Ivan kernel. So, then set z of x as a constant and xi minus x, the recenter x, okay? So this is a two-dimensional vector if this is a scalar, okay? And then the kernel, just as before. Then the closed form solution for beta hat naught and beta hat 1 is weighted least squares. The sum of the weight, z prime, inverse the sum of the weight, z xi. So you see how it emits a closed form representation. It's just the same formula of weighted least squares. And then you can do local linear regression, but just using the usual least squares formula. Of course, you will have to, quote unquote, run this regression for each value of x that you care about, okay? So it may involve running these regressions many, many, many times, okay? But that's what we're doing. And notice, as h goes to infinity, the local linear estimator approaches the full sample least squares estimator. So if you just let h go to infinity, what you're doing is just regression. So now we have an estimator that is nonparametric, but it's also, instead of connecting us to a constant thing, is connecting us to a linear thing. And, so what I wrote here is that the local linear estimator is a flexible generalization of the ordinary least squares estimator. So today I'm going to go over by a couple of minutes, so stay with me so that we can get this done. So we're not going to work out the asymptotic normality of this, of course, but I'm going to just show you the result. And the result, there's only one thing that you should pay attention to. This, in a way. It's exactly the same result as the Nadaraya-Watson estimator, except that the bias term is shorter / simpler. This is the bias term that we had before for the Nadaraya-Watson estimator, also dependent on the first derivative. And the bias of the local linear only depends on the second derivative. Okay, in particular, notice this. If the function, okay, did I write this over here? Well, no. But the bias of the local linear does not depend on the density of x, so it's called sometimes design adaptive, okay? And, if the function m, the true function, is linear, which means that this derivative is 0, then this estimator doesn't have a bias. Okay? Because this cancels out. Okay? So there are also some details that I'm not going to show. For example, you only need continuity of the density here. You don't need continuous differentiability. And then once you see this, that the f prime doesn't even show up in this expression, where it does show up in the case of the Nadaraya-Watson. So again, I'm not going to prove this, but it's important to understand the differences between the bias of these two terms. And so the local linear estimators preserves linear data. So if you now simulate things that are linear, this estimator is going to perform really well. Actually, it's just going to give you the function. If you just plug in a linear function, the local linear estimator is going to understand that. It's going to give you that. Okay. And then also, which is saying the distribution of the local linear estimator is invariant to the first derivative of m. It has 0 bias when the true regression is linear, which is what I said before. And the local linear estimator has better properties at the boundary than the Nadaraya-Watson estimator. Okay, and the important thing is that the local linear estimator has a bias of order h squared. Okay, right? Whereas the Nadaraya-Watson estimator had order OH. Okay, so that's why, as we're going to see next class when we talk about regression discontinuity, in the RDD literature, it is common practice to use local linear estimators because you're essentially estimating functions at the boundary all the time. On last slide, I said this already. These are particularly useful in RDD. Okay, and if you say, okay, now with it local linear, you could do local quadratic. Sure. In fact, you can do local polynomial estimation, and that's a topic, okay, that is part of the class that Joel teaches in the second year course. And, again, there are benefits of doing local quadratic functions, in particular, depending on what you want to estimate. For example, if you care about estimating a second derivative, okay, but then there are usual issues if you start considering polynomials that are too high in degree, that, in terms of how they affect the limited distribution of these estimators, okay? All these topics, way beyond what we're going to cover. What I hopefully want you to get out of today's class is that the Nadaraya-Watson estimator is a nonparametric method to estimate the conditional expectation of y given x, that it has asymptotic properties that are sort of like the usual ones, asymptotically normal and so on, but it has a bias term. And all this delicately depend on the choice of the bandwidth. And that the local linear approach is essentially the same, except that instead of approximating with a constant in every neighborhood, you approximate by a linear regression function, okay? So it maps really well to what we know about local linear regression. But other than that, is similar to the Nadaraya-Watson estimator. But it has different properties asymptotically, so we saw that it has differences in terms of the bias term and some of the conditions you need for the derivations. All right, that's all for today. Sorry I went over for a couple of minutes, and also that we went slightly faster today. But I we don't have the time to split this into two lectures. So hopefully you will find it useful, at least in the future. For now, I'll just move to answer questions if you have.